All right, so today we're going to really dig into large language models, but not just like chatting with them, more like how to make them really work well, like when you need them to do a lot or be super fast. So you send over this article, LLM Inference, Optimizing Latency, Throughput, and Scalability Continuous Improvement. Kind of mouthful, huh?
Yeah, it does sound a bit textbooky,
hmm
but honestly, it's really interesting stuff.
Okay, I'll trust you on that. So, like, why is all this optimization so important? I mean, is it really just to get them to run a tiny bit faster?
It's way more than that. Think of it like this. You've got this amazing, powerful tool in LLM. But if it's slow or clunky, it's just not that useful, is it?
Yeah, true. Like a fancy car that can only go 5 miles an hour.
Exactly. So optimization is about making them practical, getting the most out of them so they can actually solve problems.
Okay, now you've got me interested. So where do we even start with this? The article talks about latency and throughput. What are those exactly?
Yeah, let's break those down. Latency is basically how fast the model responds. Like when you ask it something, how quick it answers back.
So like lower latency is better then. What about throughput?
That's about capacity, how much it can handle at once.
Gotcha. So low latency is speed and high throughput is like volume.
Exactly.
But the article mentions this tug of war between the two.
Right. It's a classic trade-off. You want to go fast, you might have to sacrifice some capacity.
You can't have it all, huh?
Well, sometimes you can, kinda. There are ways to optimize for one or the other, depending on what you need it to do.
So it's about making it work the way you need it to.
Exactly. There's an example in the article. If you're handling 250 requests at once, that's high throughput. You get like 50 times the processing power. But the response time also goes up by 5 times.
Wow, so that's a big difference. How do you know which to go for then?
Depends what you're using it for. Like for a chatbot, you'd want low latency, so the conversation flows naturally.
Right, because you need those quick responses.
But if you're analyzing tons of data, like for research, then you might be okay waiting a bit longer if it means you get through it all faster overall.
Makes sense, the right tool for the job.
Exactly.
So, okay, we've got latency and throughput. What else do they do to optimize these things?
One thing is tensor parallelism.
Tensor parallelism.
It sounds complicated, but it's about splitting up the model and running it across multiple GPUs.
Hold on, so even if it could fit on one GPU, there's still a reason to use multiple.
Yeah, think of it like teamwork. If you have a huge task, splitting it up makes it faster.
So each one focuses on its part.
Exactly. And with tensor parallelism, you're creating a team of GPUs, which also lets you use models that are too big for one GPU.
Okay, I'm following you so far. Now, the article also mentions something called PP2. Is that like a type of tensor parallelism?
Yeah, it's a specific way of doing it, but it can affect that latency throughput balance. Sometimes it makes things faster individually, but not always great for huge volumes.
So even within this one technique, there are choices to make.
Right. It all depends on your specific application.
Gotcha. Always about the right tool for the job.
And speaking of tools, the article even suggests specific hardware, like using servers with NVLink or certain PCIe cards.
Whoa, okay. This is getting pretty technical.
It's about data transfer, basically. These components can handle the massive amounts of data, especially when using things like TP2.
Making sure the pipes are big enough.
Exactly. But then there's another level even deeper, FP8 precision. This one's about making the model use numbers more efficiently.
Okay, break this down for me.
Imagine you have a huge box of Legos, but you only need a few specific pieces. FP8 is like taking only those essential pieces, using smaller numbers without losing too much accuracy.
So it's like tidying up and keeping only what you need.
I like that analogy. And it saves space and makes things run faster.
Like those smaller Lego pieces are easier to connect.
Exactly.
This FP8 thing seems like a game changer.
It is, especially for large-scale deployments, when every bit of memory and speed counts.
Okay, so we've got tensor parallelism for splitting things up and FP8 for slimming down the data. Anything else these optimization wizards use?
Well, NVIDIA actually has a whole toolkit for this stuff.
NVIDIA, the GPU company.
Yeah, they have TensorRT-LLM, which optimizes models, and Triton Inference Server, which helps with deployment.
So it's not just hardware, it's the software too.
Right. They even have NM, which gives you pre-built stuff.
Sounds like NVIDIA is all in on this LLM stuff.
They seem to be leading the way. And for the really huge models, they recommend using NVLink systems to manage all the data.
Wow, they're really building the future of AI here.
It is pretty exciting to see how fast it's all developing. But now that we've got the basics of optimization, let's talk about how you actually use these optimized LLMs.
Yeah, let's get into that.
Okay, so let's talk about actually using these LLMs.
Yeah.
Because Just having them optimized isn't enough, right?
Totally. It's like having a fancy kitchen gadget, but no recipes. So how do we go from all this optimization to actually putting it to work?
Well, the article talks about different deployment modes, specifically streaming versus sequential mode.
Deployment modes. Is that like choosing between self-checkout and waiting for a cashier?
Right. Kind of. Think of streaming mode as getting the first part of the answer super quick, like when Google suggests completions before you finish typing.
Oh, yeah, I see. So it's all about that instant feedback. So what's sequential mode then?
That's about getting the whole answer, even if it takes a bit longer. Like if you ask it to write a poem, you wait for the whole thing.
Okay, so streaming is like a quick preview, and sequential is the full download. But why would you ever choose sequential if streaming is faster?
Sometimes you need the complete output to make sense of it. Like translating a document, you need the whole thing, not just bits and pieces.
That makes sense. So streaming for speeds, sequential for complete answers. But here's something I've always wondered. Does it take the LLM longer to process a long input? Like, is there a difference in thinking time?
That's a great question. And actually, the article mentions this. Turns out outputting those little bits of text, the tokens, that actually takes more time than inputting them.
Really? I always thought understanding the question was the hard part.
It seems that way, right? But the LLM has to actually generate those output tokens. It's creating something new which takes time and effort.
So even a short question can take a while to answer if it's complex.
Exactly. And that can even affect streaming mode. That first junk might be delayed if it's working on a tough response.
Okay, I see how it all connects now. But let's zoom out a bit. We've talked about optimizing the LLM itself. But what about the systems that run them? How do you make sure they can handle the workload?
You're thinking about the bigger picture now. This is where peak demand comes in. No system runs at 100% all the time, right?
Yeah, like my email inbox quiet for hours, then suddenly flooded.
Exactly. So you need to plan for those peak times. When everyone needs the AI at the same time, the article suggests aiming for 95% of your peak demand. That way you have some buffer.
Like building a bridge for rush hour even if it's empty later.
Exactly. But you don't want to overbuild either. If the system is mostly idle, you're wasting money.
So how do you find that sweet spot? What if you don't know what your peak demand will be?
That's where you use data and some statistics. There's something called a Poisson distribution that can help. It helps you predict those bursts of activity.
Okay, so data-driven decisions are key. Now there's another big decision to make. On-premise versus cloud. What are the trade-offs there?
The classic build or buy decision. On-premise means you have your own servers, which give you control but costs money for hardware and upkeep.
Yeah, I've heard those data centers can get really hot. Cloud services seem much easier, just pay a fee and you're done.
They are convenient, especially for smaller companies, but cloud services charge based on usage. So it can get expensive if you're using it a lot.
So it's like renting versus owning.
Exactly. It's about flexibility versus control. Do you want convenience or more control and potentially lower costs?
It's a tough choice, but at least now I understand what to consider. This is all way more complex than I thought. You know, we've talked about balancing latency and throughput. Is there a way to actually reduce latency without sacrificing throughput?
You've got great questions today, and yes, there are techniques for that. The article mentions something called in-flight batching, or IFB.
In-flight batching sounds like something from an airport.
It does, ha 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 ha. But here it's about optimizing how requests are handled. Imagine a line of people waiting for a service. Instead of one by one, IFB combines them into batches.
Like a carpool lane for your AI workload.
You got it. And it's not just static batches new requests can join in, like a carpool lane constantly picking up passengers.
That sounds super efficient. No more waiting in line. So does this actually reduce latency then?
Yes, by keeping the GPUs busy and streamlining things. IFB can lower latency without hurting throughput.
Okay, IFB sounds awesome. But what if you have one request with a really long input? Like a giant document, does that mess things up?
That brings us to chunked context processing. Imagine trying to eat a huge sandwich in one bite. It's easier to break it down into smaller bites.
So we should cut our LLM sandwiches into pieces.
Exactly. Instead of feeding the whole document at once, you split it up. This helps the model process it without getting overwhelmed.
Like pacing yourself during a marathon.
That's a great analogy.
Yeah.
So chunked context processing helps with those long inputs. But, we've been focusing on the server side. What about the client side? Can we do anything to help?
Oh, good point. Like, are there things we can do to make things run smoother?
Absolutely. There's something called client-side concurrency. Imagine one lane of traffic trying to handle rush hour.
Ugh, don't remind me.
But now imagine multiple lanes flowing smoothly. Even with the same volume, things move much better.
So are we talking about sending multiple requests at once?
Exactly. Instead of one at a time, you send multiple simultaneously, like creating extra lanes of traffic to keep things moving.
Like having multiple chefs in a kitchen instead of just one.
I love that analogy. Client-side concurrency helps handle more requests without slowing down. We've covered so many techniques now. Makes me wonder, is there anything else we need to think about?
I know, it's like we've opened this treasure chest of tools, but are we missing anything?
Actually, there's one more thing we haven't mentioned. It might seem obvious, but it's often overlooked. Model size.
Oh, right. Like the difference between a simple question and a depth debate.
Exactly. Bigger models need more power and take longer to respond.
So it's not always about picking the biggest one.
Right. Sometimes a smaller, more focused model is better. Like choosing the right vehicle for a trip.
Okay, so choosing the right model is like packing for a vacation. Don't overpack, but make sure you have what you need. This has been so interesting. I feel like I've learned so much.
Me too. It's amazing how much innovation is happening.
Yeah.
And how people are pushing the limits of what's possible. It really does feel like we're just scratching the surface with all this.
Yeah, with all this talk about optimization, it makes you wonder, what's the next bottleneck? What's holding these LLMs back?
Yeah, that's the big question, isn't it?
So what do you think? Hardware limitations? Algorithms? Or something we haven't even thought of yet?
Probably all of the above, I'd say.
Yeah.
Definitely need faster, more specialized hardware to handle these increasingly complex models. And smarter algorithms too, of course.
Yeah.
To squeeze out every bit of performance.
And who knows what crazy new ideas will come along as we keep pushing the boundaries of AI.
It's like we're exploring a giant uncharted territory. We see the peaks in the distance, but no idea what we'll find.
That's a great way to put it. So to wrap things up, what advice would you give to someone just starting out with LLMs?
I'd say be curious and experiment. Don't be afraid to get into the technical details, but don't get lost in them either. Remember, these are tools, and it's up to us to learn how to use them.
Right. Learn the basics, but then get your hands dirty and try things out.
Exactly. That's how
Yeah.
you really learn and discover.
And who knows, maybe you'll make the next big breakthrough.
It's an exciting time to be involved in all this.
This has been such an amazing deep dive. I feel like I have a whole new understanding of LLMs now.
Me too. It's incredible to see all the innovation happening.
Well, thanks for joining me on this journey into LLM optimization.
It was my pleasure.
And to all our listeners out there, keep those brains buzzing and keep exploring. We'll catch you on the next deep dive.